Welcome to lesson 31 on power system analysis. In this lesson we will discuss about formation of bus impedance matrix. We will start with an introduction, then we will go to the method for building Z bus matrix, and finally we will take up an example for building the Z bus matrix. On completion of this lesson, you should be able to develop an algorithm for building Z bus matrix and form Z bus matrix for any power system. Well, as we had discussed in the earlier lesson, that we need to use Z bus matrix for short circuit or fault calculation for large power systems. We had seen in the earlier lesson that we can obtain this Z bus matrix by inverting the Y bus matrix, but inverting this Y bus matrix for a large power system is computationally very expensive and time consuming. Therefore, we most of the time try to build this Z bus matrix by a step-by-step algorithm. Just like Y bus that we could build using or by just inspecting the network, we can't do the same for Z bus. That is, Z bus cannot be formed by inspection just like the Y bus matrix formation that we had done earlier. Now, Z bus matrix requires building algorithm where we add each element step by step to finally form the Z bus for the complete system. Z bus matrix is basically describing the open circuit description of the network. We will see why this happens. Now, if you recall the network equation, we can write as V is equal to V bus is equal to Z bus into I bus. So, we have written this equation in expanded form where we have a n bus power system. So, we have voltage at various buses as V1, V2 up to Vn, and we have the current injections as I1, I2 up to In. Now, these voltages or the bus voltages that we have are measured with respect to a common reference, which can be the common neutral of the generators or the ground. So, all the bus voltages are referred to that common reference. Now, these elements Z11 up to Z1n or for Zn1 up to Zn, these elements are the elements of the Z bus matrix, and we need to find the values for these elements for the system, and we do this by the Z bus building algorithm. We will see how we do that. So, now what we can do is this, that if we make all current injections 0 except at the bus P, that is, if you see this relationship here, we make I1 up to IP minus 1 0 and IP1 plus 1 to In as 0, that is, except IP we make all these current injections into the network as 0, then we will get V1 will be equal to Z1P into IP, because all the other terms are going to be zeros, they are getting multiplied by 0. So, they will be 0. So, V1 will be Z1P into IP, V2 will be Z2P into IP, Vp will be equal to Zpp into IP, and similarly Vn will be equal to Znp into IP. That is, what we will get is only the pth column of the Z bus matrix which is involved in this case. So, when the current is only IP current is non-zero, then we are seeing the relationship that we get will be something like this: V1 up to Vn is equal to the pth column of the Z bus matrix into IP. Okay. So, what do we understand from this? That if we want to compute any column of this Z bus matrix, what we need to do is open all the other bus voltages except, that is, all the other bus injections are made 0, means we have to keep the all the bus voltages, or sorry, all the buses, other buses, all the buses except bus P will be open circuited. There is no current injection at those buses except the pth bus where we are injecting a current IP. If we do this, then we will get this ZPI as VI by IPI for where Ik is equal to 0 with k not equal to p. That is, we will get all the elements of the pth column I is equal to 1 to n, that is ZPI. So, that is all the elements of the pth column we will get by keeping all the currents 0 except the pth current injection. Since all the impedance elements are defined with all the nodes open circuited except one, the impedance elements are called open circuit driving point and open circuit transfer impedances. That is, what we have done is, except for the bus P, all other buses are open. So, the impedance that we are getting here, we call them as open circuit description. That is, we get the impedances. These impedances are called open circuit driving point impedance or open circuit transfer impedance. When, that is, ZPI is equal to open circuit driving point impedance when P is equal to I. That is, ZPP is basically what we call the driving point impedance for bus P, and ZPI for P not equal to I is called the driving point, is called the transfer impedance, open circuit transfer impedance between buses P and bus I. Okay. So, this is how we can do. If we want to do this by simulation, what we need to do is, in this n bus power system, we inject a current IP into bus P and measure the voltage at all other buses, and then we can find out Vn by IP as ZPN or V1 by IP as ZP1. So, we can, Z1P or ZP1, they will be same. So, this is the way we can do it. We can simulate this experiment also by writing down the Kirchhoff's law for the network that we have and do this, though doing that reduction again will be pretty complex, and that is why we do not work this kind of a simulation for large systems. This is good for small systems, but for large system we need a systematic algorithm which we can program to run on a digital computer. Now, the diagonal element, that is Vp by Ip, that is what ZPP is what we call the driving point impedance of at point P or the bus P, and this is also equal to the Thevenin's equivalent impedance of the network at node P or bus P. So, driving point impedance is same as the Thevenin's impedance that we will get by reducing the network up to point P. Okay, so now we will get into the Z-bus building algorithm. What we do is, we start with an assumption that we already have some Z-bus matrix for say a K-bus system or a N-bus system, and we want to modify this matrix to include some more elements. That is, what we are trying to do is, we already have a Z-bus, now we are adding more elements or making it larger for the modified system. So, what we are looking at is how we are able to modify the Z bus to include other elements in the system. In general, the modifications that we can get for adding these new elements are of 4 different types. One is type 1 is adding a branch with impedance ZB from a new bus P to the reference node. That is, we are adding a new node to the already existing n bus system that we have. So, we are adding a new node P to this system, and the impedance is connected from this new node to the reference node. This is the type 1 kind of modification that we are saying. Then type 2 modification is adding a branch with impedance ZB from a new bus P to an existing bus K. That is, we are again adding a new bus P, and from this bus P we have a branch connected to some other bus K which is already in the existing network. Type 3 modification can be adding a branch with impedance ZB from the existing bus K to the reference node. That is, we are adding this branch ZB from an existing bus K to the reference node. So, this can be another kind of modification which is there. We call this as type 3 modification. Type 4 modification is adding a branch with impedance ZB between 2 existing buses J and K. So, the 2 buses J and K are existing in the already Z bus for which Z bus is available to us. Now, we are trying to add a new branch between bus J and K of this existing system. So, these 4 types of modification in general take care of all the kinds of additions or modifications that we will require in most of the cases. So, we will start with the type 1 modification, that is adding a branch with impedance ZB from a new bus P to the reference node. Now, this is the original network that we already have. This is an n bus network, let us say, and we have added a new node P from which we have connected a branch with impedance ZB to the reference node. We have taken out the reference node here to show that we are making the connection to the reference node, and rest of the network n bus network is inside this rectangle. Now, we can write down the equations for this kind of a system. Now, here we will see Vp will be equal to how much? Zb into Ip. So, if we write down the equation in this case, then we have for the existing system V1, V2, Vn which was already there. So, these zeros are basically indicating the previous values or already existing values. The Z original is the n by n original matrix that we have for the n bus system that we already have, and Ip, I1 to In are the current injections in the existing system. Now, we have added a bus P, right, and we have seen that Vp is equal to Zb into Ip, right. So, we will now get n plus 1 into n plus 1 matrix, whereas n into n original matrix is already there, and we have only one equation added, Vp is equal to Zb into Ip. So, these elements of this n plus 1th column from 1 to n will all be 0. Similarly, for n plus 1th row from 1 to n, all these terms will be 0 because Vp is equal to Zb into Ip only. So, the modification or the new modified matrix will be n plus 1 into n plus 1 matrix, which will look like this, where we have this Zb as the diagonal n plus 1 into n plus 1 element. Okay. So, this is what we need to do. So, this modification is very simple. Whatever matrix we have, we add one row and one column to it, and all the elements of this extra row and column are zeros except the last element or the diagonal element, which will be equal to ZB, the branch impedance that we are adding from the new node to the reference node. Okay, so next we will go to type 2 modification, that is adding a branch with impedance ZB from a new bus P to an existing bus K. So, this what we have is the original network is there in this rectangle. What we have is we have taken this bus K and the reference node outside to indicate the system situation. Since we have added a new node P, and we are adding this new node P by connecting it through a branch ZB to the node K. Okay, so this is what is indicated here. To the node K, we are adding this branch from the new node P. Now, what happens if the current injection in this node is IP? Then the current injection, now the modified current injection from node K will be IK plus IP, because earlier it was IK. Now we have added this IP is flowing like this. So, here into the network at node K, what will be entering? It will be IK plus P current, which will be entering, and therefore it is going to modify the voltages at all other buses. So, we will write down the equation for that. So, now Vk, as if you recall from here, Vk will be equal to Zk1 into I1 plus Zk2 into I2, Zkk into Ik, and plus up to Zkn into In. So, we are writing that expression Vk is equal to I1 into Zk1 plus I2 into Zk2 plus, now at the kth bus, what is the current which is entering? The current which is entering now is Ik plus Ip. So, we will have Ik plus Ip into Zkk plus up to In into Zkn, right. That is what we are seeing here, is that from the previous value that we had where Ip was not injected. So, we had Vk is equal to, now the changed Vk is equal to what was the previous Vk voltage at that bus plus Ip into Zkk. Ip into Zkk is what is getting added, or delta V is at bus K. Similarly, for bus P, if we want to find out the voltage, what will be the voltage? The voltage will be whatever is the voltage now at bus K plus Zb into Ip. So, this, because Zb into Ip is the drop from Vp to Vk. So, we can write this as Vp is equal to Vk0 plus Ip Zkk, that is, we can write this whole term as Vk plus Ip into Zb. Now, we can write this in expanded form, where we are putting for Vk0 the values here. So, I1 Zk1 plus I2 Zk2 up to In Zkn plus Ip into Zkk plus Zb. So, Ip into Zkk plus Zb, right. Similarly, we can write down the voltage at any other bus I as I1 into Zi1 plus I2 into Zi2 plus up to, now the current at kth bus is Ik plus Ip. So, Ik plus Ip into Zik plus up to In Zin. Okay. So, this is the way we can write down the voltage at any other bus. So, what is happening at the kth element impedance for that row is not multiplied by ik now, but it's getting multiplied by ik plus ip, because now this is the modified current injection at bus k. So if we do that, then we can write this whole thing as in matrix form as V1 to Vn Z original. Now what is happening here, for each one, whatever was the previous value that we will get from this n bus matrix, that is Z11, Z12 and so on, Z11 into I1, Z12 into I2 and so on, plus Z1k into IP. So the new voltages will get modified by addition of Zik into IP, and therefore we have this column, that n plus 1th column, where we will have the elements which will be Z1k, Z2k and so on, which is same as saying the kth column of the original Z bus matrix becomes the column here up to nth element. Similarly, we will write the expression for Vp. Here again what we will get, Zk1 into I1 plus Zk2 into I2. This is what is giving us the Vk0 term, plus Zkk plus Zb into Ip. So the n plus 1th row and column term, that is Zn plus 1 n plus 1 term, will be Zkk plus Zb, and the row n plus 1th row will be nothing but the kth row of this original Z bus matrix. So this is how this gets modified. Now again, since this bus P is a new bus, so we have now in the system n plus 1 nodes, so we will get Z bus which will be n plus 1 into n plus 1, and this is the modified Z bus which will be n plus 1 into n plus 1. So this is how we can take care of the type 2 modification, where we are adding a new bus by connecting it through a branch ZB to an existing bus K. Now we will take type 3 modification, where we are adding a branch with impedance ZB from existing bus K to the reference node. Now this, if we look at this, as from an existing node K, which is already in the original network, we are connecting a branch ZB to the reference node. Now this, what we do is, we do this modification in 2 steps. That is, what we do is, first we say that we add this ZB to a new node P. That is, already we have seen how we do that. That is, from a new node we add this branch ZB to bus K, which is same as type 2 modification, and then we connect this node P to the reference. So now this Z branch ZB is connecting the node K to the reference. This is what the this type 3 modification is. So we do it in 2 steps. So type 2 modification, add ZB from existing bus K to new bus P, and then connect bus P to the reference. So let us see how we do that. So first part, which is the type 2 modification, is very simple. We have already seen how to do it. So step 1 is to build this n plus 1 into n plus 1 matrix. Now we, in next step, we are connecting this Vp to the reference, so the voltage Vp becomes equal to 0. So this is what we do in step 2. This voltage is made 0. So now we have this as the modified equation for the system, where this is defining our system, where a branch with impedance ZB has been connected from a bus K to reference bus. The only problem here that we see is that since we have not added any new bus, so the network should be is having only n buses. So, the bus impedance matrix will also be a n into n matrix, but this modified matrix that we have is n plus 1 into n plus 1. So, what we need to do is we need to eliminate the last row and last column of this matrix. How do we eliminate this? This we do by what we call as the Qur'an's reduction technique. That is, we try to use this expression, and this expression we have 0 here. So, from this equation we try to find out the value of IP in terms of Z and all other currents. Once we get that value of IP, we can substitute that value of IP in this expression. So, everything will come in terms of only currents I1 to In, and we will get a reduced n into n matrix. Let us see how we do that. So, we write the last equation, 0 is equal to Z1 K1 I1 into Z1 K1 plus I2 into ZK2 K2 plus In into ZKN plus IP into ZKK plus ZB. That is, we are writing this 0 is equal to ZK1 into I1, ZK2 into I2 up to ZKN into In plus ZKK plus ZB into IP. So, that is what we have written here, IP into ZKK plus ZB. Now, from this we can find out the value of IP. We can take this expression on the left hand side. So, we can write this as minus IP into ZKK plus ZB is equal to this term, or we can write IP into ZKK plus ZB is equal to minus of all these terms, right, minus of I1 into ZK1 minus I2 ZK2 and so on minus In ZKN. And from that expression we can find out the value of IP by dividing or bringing this ZKK plus ZB, which we have taken on this side, that is dividing by ZKK plus ZB, this whole expression. So, we will get IP is equal to minus 1 by ZKK plus ZB into I1 ZK1 plus I2 ZK2 plus In ZKN. So, this is the value of IP that we get. Now, if we write down the expression for voltage at any bus I, then Vi is equal to I1 into Zi1 plus I2 into Zi2 plus up to Ik into Zik plus up to In into Zin plus Ip into Zik. That is, here if we see for any expression, we will get I1 into Zi1, I2 into Zi2 and so on, In into Zin plus Zik into Ip. That is what we are getting here. I am sorry. This is what Ip into Zik. Now, we know the value of Ip from here. So, we can write Vi is equal to all this term plus Ip into Zik. This term is Ip. So, Ip into Zik we can write like this. Now, we can simplify this by combining or arranging terms for I1, I2 and so on together. Therefore, we will get Vi is equal to I1 into Zi1 minus 1 by Zkk plus Zb into Zk1 into Z1k. I2 will plus I2 into Zi2 minus 1 by Zkk plus Zb, Zk2 into Z2k plus so on up to In Zin minus 1 by Zkk plus Zb, Zkn into Znk. So, this is what we will get by arranging terms for I1, I2 and all that separately. So, finally, we get this like this, that is, the new elements of the Z bus matrix can be seen as Zij new values will be Zij old values, which is this one, okay, here, minus Zik into Zkj, Zik into Zkj divided by Zkk plus Zb. This will be the new value that we are going to get for any element ij. Say for in, if we are writing, then we will have Zin, which the old value which is there, minus Zik sorry, Znk or nk into Zkn. So same thing here, that we are getting divided by Zkk plus Zb. So this is how we will get the new modified element, and if we want to write this thing in matrix form, then we have Z bus new is equal to Z bus old minus 1 by Zkk plus Zb into this column of Z1k to Znk, that is the kth column of the Z bus matrix multiplied with the kth row of the old Z bus matrix. This, if we do multiplication, this will be again a n by n matrix. So this n by n matrix that we will get is divided by this term Zkk plus Zb, that is all element of this matrix that we will get, n by n matrix will be divided by this term, and that is subtracted from the old n by n Z bus matrix. Okay. So this is how we take care of the type 3 modification, that is, we finally get a n by n matrix by eliminating the last row and last column of the modified matrix that we had obtained by including that bus P and then connecting it to the reference. Now we will go to type 4 modification, which is adding a branch with impedance Zb between two existing buses J and K. So here we have taken out two nodes J and K outside to show the connection of a new branch Zb between these buses. That is, we are adding a branch Zb between these two buses, and of course we have taken out reference to indicate this. So this is the original network, that n bus network. We have just taken out these two nodes and we have shown that we are adding a new branch Zb here. Now if we look at this, then what we have, Ij current injection at bus J, Ik current injection was at bus K. Now when we add this branch Zb, then we are assuming that the current direction Ib is like this, then we will get the current injection into the network at bus J now will be equal to Ij plus Ib, and at bus K now it will be Ik minus Ib, because Ik is coming here, out of which Ib goes like this into the network like this, whereas the current which comes here is Ik minus Ib, and this current becomes Ij plus Ib. So we can now write the expression for any voltage Vi for this system as Zi1 plus up to Zij. Now for bus J, what is the current injection? This is Ij plus Ib. I am sorry, this should be dot dot dot, there is no, this L is not there, this should be dot dot dot, plus Zik at bus K. What is the injection? Ik minus Ib, so Zik into Ik minus Ib plus dot 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 Zin into In. So this is the voltage that we will get. This L in here is not actually L, it should indicate dot dot dot. Okay. So now we are writing the same expression here by taking the terms of IB together outside. So, we have Vi is equal to Zi1 into I1 plus up to Zij into Ij. Again this L is dot dot dot. Okay, this has come wrongly typed. So, this should be dot dot dot, not L. So, this dot 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 plus Zik plus dot 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 plus Zin plus what we will get Zij Ib minus Zik Ib. So, Zij minus Zik into Ib. This is what we have got now for this Vi. Now, we can write the same thing for Vj. Vj will be Zj1 I1 plus up to Zjj Ij plus Zjk Ik plus all this plus Zjj minus Zjk into Ib. Okay. That is, we are saying at this bus, what is the current injection at bus J? The current injection at bus J is Ij plus Ib. So, we will get this Ij plus Ib. So, Zjj into Ib, right, and it at bus K what we have Ik minus Ib. So, Zjk minus Ib. So, this we have written as Zjj minus Zjk into Ib and the end, right. Similarly, for any bus other bus K, we can write this in a similar way like this, where again the at bus K we will be having Ij plus Ib. So, we have Zkj into Ib minus this will be at bus K we will have Ik minus Ib. At bus K we have Ik minus Ib. So, we have Zkk into Ik minus Ib. So, Zkk Ib will be negative. So, we are adding it here in the end. So, what we get is we are writing this as this term, and what is Vk equal to? Vk is equal to, if we see from this diagram, this voltage will be equal to the voltage at this point, that is Vj, plus the drop here which is Zb into Ib. So, we can write this Vk is equal to Vj plus Zb into Ib. What we can now do is we can take all these terms, that is on this side, then we will get this Vk minus Vj minus Zbib will be equal to 0, or we take this Vk term on this side. So, we will have Vj minus Vk plus Zbib is equal to 0. So, we are writing 0 is equal to, this is Vj minus Vk. So, we are writing minus Vk here plus Vj, this is minus Vk, this whole expression with a negative sign. So, minus Vk plus Vj, this is Vj term that we have, this expression that we have. So, plus Vj plus Zb into Ib. So, this is what we are going to get. 0 is equal to this much. This again we can combine the terms of currents I1, I2 and so on separately. Then we can write this as Zj1 minus Zk1 into I1 plus this again L is not L, this should be dot 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 plus Zjj minus Zkj into Ij plus dot 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 plus Zjk minus Zkk into Ik plus this will be again dot 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 plus Zjn minus Zkn into I1 plus this term that we are getting for IB. That is, when we add it for IB, then we have this term for IB, this term for IB, and this term for IB. So we have ZKJIB minus ZKKIB. Sorry, this is again a minus term, so this will be ZKKIB minus ZKJIB plus ZJJIB minus ZJKIB plus ZBIB. So this term is what we are getting here, right? We can write this whole thing in matrix form, where this expression goes as the n plus 1th expression. So we have V1 up to Vn, this is the original matrix, and we have IB terms for all these voltages are coming as multiplied by IB into Z ZKJ. For Vk we are getting, or Vi we can write, this will be ZJJ minus ZKJK. That is, what we are getting is the column of jth column minus the kth column is coming here, that is multiplied by IB. So we are jth column minus kth column of the original Z bus matrix, this multiplied by IB. So n plus 1th term is jth column minus kth column of the original matrix will be coming here. Similarly, in the last row that we have, jth row minus kth row is coming for this last expression. This is jth row terms are here, j minus k. So jth row term minus kth row terms are coming here. So the n plus 1th row here, we have 0 is equal to, these terms will be row j minus row k terms, n number of such terms will be there, plus n plus 1 and n plus 1 term which will be there will be for IB, and that term is this one. Okay. So we have now this term here. Now again, as we have seen, we have a n plus 1 into n plus 1 matrix, where we have last term as 0 here. So using this last, we need to eliminate last row and column, because there is no additional bus in this system. The total number of buses in the system still remains as n. So the Z bus matrix is going to be a n into n by n matrix only. Therefore we need to eliminate this n plus 1th row and n plus 1th column, which we again do using the Cron's reduction. So if we do that, then again we will get the new Z bus matrix will be equal to old Z bus matrix minus 1 by this term ZJJ plus ZKK plus ZB minus 2ZJK we are writing here, because we are saying that ZJK and ZKJ are same, they are equal. Therefore this minus 2JK is coming here, as well as here we are writing the same thing. This multiplied by the n is to 1 column, which is the jth column minus the kth column terms, multiplied by the n is to 1 row, which is jth row minus kth row for each term. Okay. So this again, this whole term is going to be n into n matrix, which we are subtracting from the old n into n matrix, and therefore the new Z bus is going to be n into n matrix. So all these modifications that we have done are, we have summarized here. So the type 1 modification is reference node to a new bus P, that is from the reference node we are connecting a branch with impedance ZB to new bus P, and this modification results in a n plus 1 into n plus 1 matrix, where the n plus 1th row and column are all zeros and the diagonal element is equal to ZB. Similarly, for type 2 modification, where we are connecting a branch with impedance ZB from a new bus P to an old bus K. So, here we will get this kind of a network, which we have seen results in this kind of a modification. Z original, the n plus 1th column is the kth column, that is the bus to which this new branch is getting added. N plus 1th row is the kth row, and the diagonal element for n plus 1th row and column is ZKK plus ZB. Similarly, for type 3 modification, we are adding a branch with impedance ZB to reference node, and this is shown here. We do it in 2 steps. First, connect this branch from bus K, existing bus K, to a new bus P, and then connect that bus P to the reference bus. The fourth type of modification is existing bus J and existing bus K are connected by a new branch with an impedance ZB. This is what it is. We have 2 existing buses and ZB branch is connecting this. Okay. So, we get this new matrix like this, and then we do the Qur'an reduction to eliminate the n plus 1th row and column and get finally the n is to n modified Z bus matrix. Okay. So, now we will take up a small example to see how we can build the Z bus matrix for any power system. So, again we are taking an example which is 2 synchronous machines connected through a 3-phase transformers to a transmission line as shown in figure. The ratings and the reactances of the machines and transformers are machine 1 and 2 100 MVA 20 kV. The XD double dash, which is same as X1, that is the positive sequence reactance, which is same as negative sequence reactance, is equal to 12% or 0.12 per unit. X0 is 5% and Xn, the grounding reactance, is 4% for this generator. The transformers T1 and T2 are 100 MVA transformers, that is the base we will choose as 100 MVA only. The transformers are 20 kV delta to 400 kV star, and the reactance is 8%. On the chosen base of 100 MVA, 345 kV in the transmission line circuit, the line reactances are X1 is equal to X2 is equal to 15% and X0 is 50%. Find the positive sequence bus impedance matrix by means of Z bus building algorithm. Now, since we have chosen here the base kV as 345 kV, so we need to modify the reactance of the transformers to this base, and if when we do that, then instead of 8% it will come out to be 7%. So, we have got the positive sequence matrix for this system shown here, where this is the synchronous machine 1, this is its positive sequence reactance, this is the transformer T1, its reactance, positive sequence reactance is 7%, that is 0.07 per unit. This is the transmission line, its positive sequence reactance is 15%. This is the transformer T2, its positive sequence reactance is 7%, and this is the synchronous machine 2, its positive sequence reactance is 12%. Now, we have put these elements as 1, 2, 3, 4 and 5, and sequentially we will build the Z bus matrix for this system. So, what we do is initially we will always start building the Z bus matrix where we have one element which is connecting one bus to the reference bus. So, always start with an element which is connected to the reference. So, if we see that we have this element 1, this voltage source will be shorted. So, with this element 1 is connected to the reference. Okay. So, we start with this element which is connected to the reference. We can also start from this side this element connected to the reference. So, either of the two we can start with. So, we have started with this. So, we have first element that we have got is connecting, element number 1 is connecting node 1 with the reference. So, we will get a 1:1 matrix for this, which will be simply ZB, because initial matrix that we have here is 0:0, and the row and column for this first will all be, those will be not there. So, we get start with J 0.12, that is, if we go back this is the thing that we have, this row and column, since the original matrix itself is 0, there is no elements. So, we have only this ZB coming into picture. Okay. So, first is J 0.12, which is the impedance of ZB matrix. Next step is add branch 2 between bus 1 and bus 2. So, again this is adding a new bus to an existing bus. So, this is type 2 modification. Again we do the same thing, that is the row n plus 1 row and column will be whatever was the value for row and column of bus 1, which is to which we are connecting this node, and this term will be equal to ZB plus Z11. So, Z11 was J 0.12 and ZB is 0.07. So, this is the value we will get in this case. Again, when we add branch 3, which is between bus 2 and 3, again we are adding a new bus, bus 3, connecting this branch to an existing bus 2. So, again the same type 2 modification. So, the column, row and column, n plus 1th row and column, that is third row and column here, are same as the row 2 column, row and column, and this element will be again ZB plus Z22, that is 0.19 plus 0.15, that is equal to J 0.34. Again add branch 4 between bus 3 and 4, a new bus is added connecting to an existing bus, again type 2 modification. So, again the fourth row and column are same as the row and column for the third bus. So, this is the column for third bus which is coming here, this is the row for third bus which is coming here, and this will be ZB plus Z33, Z33 is 0.34, ZB is 0.07. So, we get J 0.41. Now, we are adding branch 5, which is between bus 4 and the reference, that is from an old bus to the reference. So, this is the type 3 modification that we have to do, that is from an existing bus to the reference. So, using this relationship that we had written earlier, we substitute the values here, Z old minus this is Z44 is 0.41 and ZB is 0.12, and this is the fourth row, fourth column and fourth row like this. Put the values here. If when we do that, we get this is the old Z bus minus this term, which gives us the final matrix as this. So, this is the way we build the Z bus matrix for any power system. We go step by step, adding one element at a time, and as we have seen, to start with, we always start with an element which is connected to the reference. So, with this we finish this lesson today, and in the next lesson we will see how we use this Z bus algorithm for asymmetrical fault analysis. So, thank you. welcome to lesson 32 on power system analysis. In this lesson we will discuss about asymmetrical fault analysis using Z-bus method for large power systems. As we had discussed in the earlier lessons, we have seen how we can use the Z-bus algorithm for solving symmetrical faults for large power systems. In this lesson we will try to extend that method for solving for asymmetrical faults. Well, we will start with an introduction, then we will talk about Z-bus matrix formulation for sequence networks, because we know that for symmetrical faults we do the symmetrical component analysis and we get the positive, negative and zero sequence network for the system. So, we will talk about formulating Z-bus matrix for the sequence networks. Then we will talk about how we use this Z-bus for the sequence networks for finding out or for solving the asymmetrical faults on large power systems. And finally, we will take up an example to show how this is done. Well, on completion of this lesson, you should be able to develop algorithm for building Z-bus for sequence networks. You should be able to develop algorithm for asymmetrical fault analysis using Z-bus method. So, and for finding out the values of post fault voltages at different buses, we can use this relationship. So, again this is V0 S1 minus this relationship that we had got there. So, this is the sequence values that we have got. Similarly, for 3 and 4 also we will get the values by substituting the values from the impedance matrix and the fault current that we have calculated. We will get these sequence values. Once we have got the sequence values, we can transform them to get the phase values. So, this is how we can calculate the fault current and the post fault voltages at all the buses, and knowing the impedances of the lines or the other equipments, we can find out the fault current flowing through each element of the system. So, with this we have completed our short circuit analysis or the analysis of a faulted power system, where we have considered both the symmetrical faults, asymmetrical faults for small systems by using the sequence network or using the Z-bus algorithm and Y-bus algorithm for large systems. So, with this we finished today, and we will talk about the power system stability in the next lessons. Thank you very much.